Hi, so in this video we're going to be looking at the sum and products of roots of a quadratic equation, and what this is some properties we can use if we know the roots or the zeros of a quadratic equation. We can use that to figure out what the original equation was, and there's a fair bit of algebraic manipulation in this, and in the next lesson this week we'll extend it to higher order polynomials of the syllabus documents say to do for cubics and quadratics. So first let's just start off with a general form of a non-monic quadratic, right, which would be something like this. Something x squared plus something times x plus a number by itself. And we're going to set this equal to an expression where we know the roots. So here we're going to use some Greek letters, just so we don't get confused with the pronumerals. So I'm going to use alpha for one of the roots and beta for the other root. Right, so if you set this expression equal to 0, then when x equals alpha it gives you 0, when x equals beta gives you the other one. Right, but if you would expand this out, you'd get x times x is only x squared, which is monic. We don't have this factor a here, so if we put that factor a out the front, right, if you expand this, then both of these expressions, right, this right one, when you expand it, it'll be x times x squared, it'll be times a will be ax squared plus something times x plus something by itself. So we're going to expand this right hand side out and then get it to match up. See what happens with the b's and c's and a's and the alphas and betas. So if we look here and use FOIL, we've got x times x squared minus alpha times x minus beta times x, and then negative times negative is plus alpha beta. Now it's actually going to be easier if we divide throughout by a, because then we don't have to deal with this factor here. So we're actually going to divide this by a, and so if we divide that by a, we've got to divide throughout everything by a on both sides. A divided by a, divide out, a divided by a. So now on the left hand side we've got x squared plus b over a x plus c over a equals x squared, and we've got minus alpha minus beta, so lots of x, so that's a common factor, minus of alpha plus beta, lots of x, and then plus alpha and beta there. So because we divided throughout by a, you can see here that on both the left and the right hand side, so the left hand side was the general form of a non-monic, which we've reduced to a monic, and the right hand form is if we know the roots, we've expanded it out, and we've got x squared equals x squared here, right? So we don't really need to touch that. But now, if you look here at the coefficients of x, you've got b over a is the coefficient of x, and you've got on this side negative alpha plus beta is the coefficient of x. So because they're both the x squareds are equal, and then these are the coefficients of x, these two things are going to be equal, right? So negative alpha plus beta equals b on a, and because we're investigating the sum and the product of the roots, alpha plus beta, remember alpha and beta were the roots of our quadratic equation, so we just want to have an expression for the sum, which will be alpha plus beta by itself. So to get rid of that, we'll times both sides by -1, so -1 times negative 1 becomes positive. So the sum of the roots of a quadratic equation, right, if we know what they are, alpha and beta, if we add them together, we'll get timesing b on a by negative, whoops, we will get, sorry, this is all in the way. Why has it started typing? Negative b on a. If we do the same thing and we look here, we've got c on a is the constant term in the general form when we've divided through by a, and here the constant term is alpha beta. So alpha beta in between them is times, so this is the product. The product of the roots, alpha beta, the pink one here equals the pink on the other side, is c on a. So like I said earlier, one application we can use for this is if we know the two roots, alpha and beta, we know that they add to give negative b on a, and then they multiply to give c on a. So we can add them and we can multiply them and get these two expressions, and then we can use that to find b, a, and c, and then therefore determine the equation of the quadratic. So what I'll do first, before we go and do the questions along there, is that we'll just investigate this first. So let me make an equation. Let's say we've got y equals x squared plus 5x plus 6. And let's just check that this all works out. So here, what's the coefficients in general form? You've got the coefficient of x squared is 1. The coefficient of x is 5, and the constant term is 6. So just like if you're a, b, and c, right? Just like you'd list them out like if you're putting them in the quadratic formula. So let's look at what happens if we calculate negative b on a. So negative b on a equals negative 5 on 1, which is negative 5. And what happens if we calculate c on a? We get c on a is 6 on 1, which is 6. So what we're going to do now is find the roots of the equation and see if when we add them we get negative 5, and when we multiply them we get 6. So if we were to factorize, this quadratic equation, right, it would have factors 2 and 3. So we'd have x plus 3, x plus 2 is equal to x squared plus 5x plus 6, and we'll find the roots when this equals 0. So x equals 0 when either this equals negative 3, so we'll call that first root alpha. Alpha is negative 3, or it equals 0 when this one's 0, which is when x equals negative 2. So we'll call this one beta. Right? So just like you would do if you're finding the roots of the equation, right? But rather than just saying, you know, the solution is x equals this or this value, we're just giving them separate names, alpha and beta. So let's add them together. So if we do alpha plus beta is negative 3 plus negative 2, which is negative 5, right? Which was the same. Right, we got negative 5. So that one worked. When we calculated negative b on a, we got the same as when we added the roots. Okay, and let's also check the product of the roots. So when we multiply, alpha times beta is negative 3 times negative 2, which is 6, right? So we've got the same thing. Also worked when we multiplied the roots, we got c on a. Okay, so now I'll start doing the questions in the slide panel. And so the first one is, we don't actually know this equation, y equals, this form here. We do know the roots, and so we can use the roots to figure out what a, b, and c are, and therefore the equation. Right? So this is now example 1. So we've got the roots, so we'll call one of them alpha. Alpha can be the first one. 7 plus root 17 on 4. And we'll call beta the other one, 7 minus root 17 all over 4. So we can first add them. So alpha plus beta will be 7 plus root 17. Now, because they've got a common denominator of 4 already, I'm going to write them. If we're adding two fractions, we can add the numerators. Plus beta, the numerator is 7 minus root 17. So plus root 17 minus root 17 cancel. So we've got 7 plus 7 is 14 over 4, which simplifies to 7 over 2. And we know that alpha plus beta equals, up here, negative b on a. So here, 7 on 2 is negative b on a. I'll just pause and leave that there, and we'll look at c on a and see how they connect. So next you've got the product of the roots, alpha times beta, which would be 7 plus root 17 on 4 times 7 minus root 17 on 4. So if we multiply them, well, let's do the denominator first, that's easy. We've got 4 times 4 is 16. And you'll notice if we multiply the numerators, there's actually a difference. It will turn out to be a difference of 2 squares, because we've got 7 plus root 17, and we've got 7 and root 17, the same thing with the minus in the middle. So we'll end up with 7 squared, which is 49, minus root 17 squared is 17. 49 minus 17 is 32 over 16, which of course is 2. But this equals the product of the roots, alpha beta, equals c over a. So notice here, they both have a denominator of a. So see how this one here, 7 over 2, is negative b on a. So this is currently 2 over 1. But if we represent it as something over 2, and that's c on a, then we can see that a is 2, and then b and c will become evident then. So 2 over 1 we can change into 4 over 2, so a's are our denominators. So c will be 4, and negative b will be 7. So if negative b is 7, whoops, I'm always bumping things on this tablet. If negative b is 7, then b must be negative 7, right? So we've figured out that a is 2, b is negative 7, and c is 4. So they're all the coefficients. A is the coefficient of x squared in our quadratic, so we've got 2x squared. B is the coefficient of the singular term x, and then c is the constant term. Right, so if you wanted to check that, you could look at this equation here, right, that we've figured out, and go a equals 2, b is negative 7, c equals 4, and go and use the quadratic formula, and then if you get the quadratic formula correctly, you should get x equals 7 plus or minus root 17 on 4. Okay, so the next ones are really just a lot of kind of fiddling algebraic manipulation. We've got I might write this down at the top. We've got a polynomial 2x squared minus 4x minus 70. So first for I, we're going to find the sum and products of the roots. So looking at this polynomial, right, this one's quadratic, but again, like I said, next lesson we'll go a bit higher order, higher degree. We've got a equals 2, b equals negative 4, and c equals negative 70. And so the sum of the roots, alpha plus beta, is negative b on a, which is going to be negative b is negative 4, on a is 2, negative 4 is 4, and 2 is 2, so that's the sum of the roots. And the product of the roots, alpha times beta, will be c on a, which is negative 70, on 2, which is negative 35. Right, so that's just using the expressions for the sum and the product. So now for the next part, we've got 1 on alpha plus 1 on beta. Right? So notice we don't know what alpha and beta themselves actually are, right? Now because we have the whole polynomial here, you could use quadratic formula and figure them out, right? You could figure out what alpha is, one of the roots, and beta the other root, and go 1 over alpha, 1 over beta, right? But the purpose of this question is that we can use this information from part 1 up here, where we do know the sum and we do know the products. So notice here we don't know either of these separately, but what we can do with this fraction is manipulate this fraction so that we do see these values here and here, right? So often, you know, just generally in algebra, if you have say a fraction, you don't really like them being separated, you want to group everything together, so you'll find a common denominator. So if you're finding a common denominator here, you'd look at alpha and times this one by the other one by alpha, and then look at the denominator here is beta, and times, so cross multiplying, oops. So now we get 1 times beta is beta, plus 1 times alpha is alpha, and common denominator of beta times alpha, and of course order of multiplication we can switch, alpha plus beta, and same with the order of multiplication. So now we do see alpha plus beta, the sum of the roots, and alpha beta, the product of the roots. So we can, and we already have these values up here, so we can exchange alpha plus beta, right, with 2, and alpha beta we know is negative 35. So we've got 2 on negative 35 is equal to 1 on alpha plus 1 on beta. So the next one is a bit tricky. The first one you might have had a look at that and how to go. Let me try multiplying, get a common denominator, and then lo and behold you end up with it. 2 expressions you did have. So this one's a bit more difficult, and you might not be as intuitive to just figure out, but once you see it, hopefully it'll make sense. So we want alpha squared plus beta squared. So again, we don't know alpha by itself, so therefore we don't know alpha squared. We don't know beta by itself, so we don't know beta squared. What might look close to this is we do know alpha plus beta. So let's just have a little scribble around here. We do know what alpha plus beta equals. So alpha plus beta, if we squared that, then when we expand this out, we'll end up with a alpha squared, and we will have a beta squared, right? If you perfect square, you've got alpha squared plus 2 alpha beta, plus beta squared, right? So alpha plus beta, we do have a value for, and if we square whatever that is, then we'll end up with this expression, which is close, right? We've got alpha squared and we've got beta squared. But we've also introduced this extra little bit, plus 2 alpha, right? So if we were to move this to the other side of the equation, then you can see here that alpha squared plus beta squared is actually equal to alpha plus beta all squared minus 2 times alpha beta. And we do have expressions for alpha beta, so we can square it. And we do have an expression for alpha times beta, so we can minus 2 lots of it, right? So when you've got two things squared separately, you can actually figure out an expression for this by squaring it, but then subtracting away, squaring them added together, but then subtracting away. Let's get rid of this now. That extra term you introduce when you expand that, right? Because when we square the whole thing to get alpha squared and beta squared, we've introduced plus 2 alpha beta, so to even out with that, we've got to subtract it away. Right? Now it's just substitution, right? So like before, we've got alpha plus beta is 2, so we can substitute that in there. 2 and then square it. Minus 2 times alpha beta. Right? And we've got alpha beta is negative 35. And what's that? 4 plus 70 is 74. Okay. Last problem for this video, we've got find the value of k if, so notice this is quadratic, k squared minus something lots of x plus k plus 1. That whole thing is the constant term. And there's also some extra information, the roots are equal. So let me write this expression out. K squared minus 7x plus k plus 1 equals 0. So let's start like we did before. We'll write out what a, b, and c are. So a is this value k, b is this coefficient negative 7, and k plus 1, this whole thing here, right? There's no x or x squared attached to it, so that's our value of c, k plus 1. So if we were to then go and find the sum of the roots, we'd find alpha plus beta equals negative c on a. But there was an extra piece of information. It said that the roots are equal, right? So that means alpha and beta are actually equal each other. Alpha equals beta. So what this means is we can, everywhere we see beta, we can replace it with alpha. So this is actually alpha plus alpha equals negative c on a. So that's like terms. 2 lots of alpha equals negative c on a. So what actually is negative c on a? We've got negative c is k plus 1 all over our value for a was k. So if we expand this out, we've got negative k minus 1 on k, sorry, and that was 2 alpha. So then if we divide both sides by 2, we've got alpha is negative k minus 1 on 2k. Alright, so let's do similar for the product. We know that the product of roots is alpha beta equals, my apologies, that should be negative b, shouldn't it? So this whole numerator is going to be wrong. Knew that because I was like, no, that should be c on a. Sorry, this should be negative b on a, and b is negative 7. That'll make it a bit easier. So we've got negative, and b is negative 7, which is negative is positive, so alpha is 7 on 2k. Alright, so let's continue up here. So alpha times beta, and remember alpha and beta were equal, so we've got beta will replace with alpha. Alpha times alpha is c on a, and so alpha squared is c on a. Alpha squared is c on a. Our value for c was k plus 1, and a is k. But now alpha squared, well, we have this expression for alpha here, right? This expression here, alpha equals this thing, we can substitute into here. So because we've got this other expression for alpha, we've got 7 on 2k all squared equals k plus 1 on k. Right, and now we've got an equation where the only unknown is k, so we can hopefully solve this equation, right? So we use what we knew about the sum and the product of roots to develop two equations, including the information that the roots were equal. Meant we could get these two expressions that we can solve simultaneously. Okay, so now it's just solving this equation. So if we're squaring, we'll square the whole thing. 7 squared is 49. 2k, the whole thing squared. 2 squared is 4. K squared is k squared. Okay. Now here, so there's a few ways you could kind of go from here. I'd notice that I've got a k in both of my denominator, so I'd times this side by k. If I times this side by k, I've got to times this one by k, and that means 1k over k will divide out, and k and one of those k's will divide out. So you got 49 on 4k equals k plus 1. Then to get rid of the denominator, multiply that up. I'm going to just kind of move over here. So I've got 49 equals, if I'm multiplying the 4k up, I've got 4k outside of k plus 1. Expanding 4k squared plus 4k, collecting everything to one side, so minusing 49 from both sides, and I guess probably quadratic formula to solve this. So we've got I'll use green for this because this is up here. A, B and C was for this equation, and then from that equation we developed an equation to figure out what k is, but this will be a different A, B and C. So now this is A, B and C for this equation. To find k is 4, B is 4, and C is negative 49. So k equals negative b plus or minus b squared minus 4 times a times c all over 2a, which you'll recall is on your formula sheet. So negative 4 plus or minus I can do it in my head. 4 times, so negative times a negative will be a positive. 4 times 4 is 16 times, let's just, by the time we do, let's do this the safe way. We've got 16 plus 4 times 4 times 49. Oh, that's nice. 800. all over 8. So 800 is root 400 times root 2, and root 400 is 20. Now, this was something in the test we just did. A lot of people were dividing throughout incorrectly. So I'm going to take the extra step to actually factorize the numerator. Right? So 4 and 20 have a common factor of 4. So you've got, I'll keep the negative 4 outside of negative 1 plus or minus 5 root 2 all over. And if you factorize 8, so we have 4 as well, 4 times 2, you're dividing out 4 over 4. So that means k is negative 1 plus or minus 5 root 2 over 2. So, I guess the question said find the value of k here if the roots are equal. Well, there's actually two values of k. So this big clunky value here, right, if we connect this back to the original question, right, if you were to go negative 1 plus 5 root 2 on 2, so that's k, x squared minus 7x plus k was negative 1 plus 5 root 2 on 2 equals 0. Right? If you were to find the roots of this equation, they would be equal. That's about the whole point of all that we did. But there was two solutions, so the same thing if you found, if you calculate negative 1 minus root 5 on 2 as a value for k, and sorry, the constant was actually k plus 1. So this is k plus 1. Right, if you found the roots of this quadratic, right, this was our value for k, x squared minus 7x plus k plus 1 equals 0. If you found the roots of that, then they would be equal. Right, so this question is done because it's similar to the style in the textbook. There's often ones where, you know, there's like some paranumeral like k, and then you have to set up some equations using the information you know, and then solve something simultaneously. So that one was a bit involved. Alright, so like I said, next lesson this will lead into doing a similar thing with higher order, so cubic and quartic equations. There will be a formula on the formula sheet. It's specified for cubics though, but I'll show in that video how you can use the cubic one to figure out the quadratic and the quartic power of 4 one. So this bit, where are we? The sum and the product of the roots, right? That the sum is, I should have emphasized this a bit more, right? So this is for a quadratic, the sum and the product, negative b on a and c on a. You might want to just rote learn that, but they're not exactly this on the formula sheet for cubics, but you can, there is kind of like a pattern, and you can look at how they're written for them for cubics and then get the quadratic ones, but I'll show that in the next video. But that's all for this one. Alright, bye.